All right. So before we get going, wanted to mention a couple things. So that Excel assignment's due by the end of the day today. I had a couple people kind of send me some files the last couple of days to look over things. So looks like at least the ones that have talked to me are on the right track. But I also was talking with someone brought something up, and I try to take feedback. So I'm always listening to ideas. I went to the YouTube page, and for every single one of these videos, at least post the first exam, I kind of put down what that class was about, like a little synopsis in the description. So if you're going back and trying to find, a specific topic, this should hopefully make it a little bit easier. I also, on the lectures, back to the first exam, and I'll update these as well. I just didn't have time to kind of get through all of them. Kind of add some names so you can kind of see what the different, what's contained in every single week's lectures. So as we get closer to the exam and as you're kind of working on homework, so you can go back and it's a little bit easier to find things, okay? All right. So we left off kind of talking about hypothesis testing when we have a known population variance and we're trying to, all we have is a sample variance, and we're trying to figure out whether or not we can reject or we fail to reject certain values. So kind of jump back into it, and as we go through the example, I'll kind of do a little bit of a review. So let's say we had this example where we want to test for whether or not the mean retirement age is greater than 67, right? We get 25 individuals, we get a sample size of 71, so we sample mean of 71, so we have a sample size and sample mean. We are somehow told, or we somehow know the population variance based off of previous data. What would the p-value be for this hypothesis test? Well, first of all, we haven't even written the hypothesis test down, so the first step is identify what that is. So if we want to test for whether or not the mean retirement age is greater than 67, so whatever we want to test for, that's our alternative hypothesis. So we're thinking, is that mean retirement age, oh, I grabbed the wrong marker, hold on. I know the black one's a little bit easier to see. So is that mean retirement age greater than 67? So we'll assume the opposite is true, kind of stack the deck against ourselves, which is that true mean is less than or equal to 67. Right? So we've got what type of tail test? If we look at our alternative hypothesis, there's a greater than sign. So we have a greater than, or what we'll end up calling, hopefully as we work through more examples, it'll be clear, a greater than or a right tail test, okay? So what we're gonna know is, if we look at these sample means, if we're assuming kind of this value of 67 being like the lowest value in that range, we'll assume that the true mean is 67. Our sample mean should be normally distributed around that value. Okay? Now we saw a sample mean of 71, right? So if we want to find the p-value, well, the p-value, the kind of the definition is the probability that you found the sample mean that you did that was as far away from the assumed true mean as it was, or anything further away. So the probability that we see a sample mean as far away from the assumed true mean as we did, or anything further away that would go even more against this null hypothesis. So this area represents kind of our p-value here. All right. So how can we find that? Well, if we know this is a normal distribution, we can turn that into a standard normal distribution. If I can find the z-score that corresponds to that sample mean of 71 that I found, well, then it's pretty easy using those tables to find that p-value. Now, it'll be a little tricky in that once I find this z-value, or what we are calling a z-statistic or test statistic, when I look it up in the table is going to tell me the area to the left. I would then have to, subtract it from 1. Okay? So how do I get that z-statistic? So if we go back to last class, we had this equation. Let's see if I can find it. right here, right? Here's our test statistic or our z-statistical equation. So we take the sample mean, which ours was 71. We'll take the assumed true mean, which that comes from your null and alternative hypothesis, so 67. We were told the population variance was 81, I think, and then our sample size was 25. So we go back to the problem that we were just working on, right? We plug all of our values in, and we get a test statistic of 2.22, right? So, right, our test statistic now we know 2.22. Right? We can look that up in the table. It'll tell us the area to the left. So let's go ahead and do that. Pull open our standard normal z tables. Scroll down here. So this is the 0.02, so 2.22. The probability of seeing that z-score or less is 0.9868. So this is 0.9868. Right? We wanted the area to the right, so we'll simply subtract that from 1. Okay? So for a right-tailed test, it's a little bit more work to get our p-value because it's the area to the right, so we have to look up something from the table and then subtract it from 1. Okay? Once I have that p-value, so that's what, 0.0132, I can start to think about what levels could I reject this null at? So if my p-value is less than alpha, that's when we said we reject. So 0.0132 ended up being our p-value. So could we reject at an alpha of 0.05 or the 5% significance level? Yeah, so we can reject at that level. What about 0.01? No. Just barely not, right? So there we would say we failed to reject. Right? Now remember, these alphas correspond to significance levels. So the 5 and 1% significance level, or said differently, the 95 and 99% confidence levels. So with 95% confidence we can reject, but with 99% we fail to reject. We can't quite say it with 99% level confidence. Okay.
So rejection is what we want?
I mean, I don't want to say it's what we want, but in the idea that if I, like, let's set this example up. If I truly believe that the mean retirement age is greater than 67, right? And I'm trying to use this to like push a certain policy or something like that, well, then yeah, if I can't reject the null that we had, which was that it's less than or equal to 67, if I can't reject that, no one's going to listen to me about my policy to like, I don't know, increase aid to, elderly, something, whatever the policy is, huh?
Increase social.
Yeah, exactly, right? Something like that. So, usually what we want to test for, what we want to find, we were doing that because we had an idea in mind. So yeah, we do kind of want to reject the null. It's probably not appropriate to say that we do want to, but more often than not, like that's why we're doing the test. We're trying to rule out this is a potential value. Here I can say, I can actually with 95% confidence reject that their mean retirement age is any value of 67 or below, which is, useful. And a lot of, depending on what I'm trying to do.
So when you fail to reject, the null is true?
Yeah, so, a true statistician would tell you not to think about it as though the null is true. They would tell you to think about it as though we don't have any sample evidence to show that it's not true, right? I mean, but you can think of it that way. That's fine. But yeah, if we fail to reject it, like we don't have enough evidence to say that it's not true. Right? Or based on the evidence, it is not unlikely that it's true. Those are good questions. Okay, so we worked through this one, kind of walked through that. Right, we had that p-value and we just kind of talked about it up on the board. So let's go through another example, right? So let's say we've got some group states that average back-to-school spending is $606.40. you think that it's just different than this amount, right? You think maybe you're not sure. So a lot of the times the two-tailed test, this is when you're like, well, look, I don't know, it could be lower, it could be higher. I just think that it's some value. I think it's either a lot, anyway, maybe I say like, I think it's a lot higher than this, or I think it's a lot lower. I'm not really sure which one it is, but I don't think it's this amount. So if I wonder, if I'm testing for whether or not back to school spending is different than this stated amount by this group, last class I said if we see this kind of terminology of different than, we should automatically be thinking about a not equal to sign. Because you're saying that it's different than or that it differs from this amount is just saying, is it not equal to $606.40? So that's what we're trying to find. So that's going to be our alternative hypothesis. So we're going to assume the opposite is true, which is that it's exactly equal to that reported amount of $606 by this trade group. All right? So we go out, we take a sample. So first of all, what type of tailed test do we have here? We have a not equal to sign. That was what we said was a not equal to test or a two-tailed test. Yeah. Because seeing evidence above or below that assumed true value would go against the null, right? Because the null is that it's literally just this one value. So if I see something above or below that value, that goes against the null. So I take this sample of 30, I find a sample mean of 622, and I have a known population variance. Okay? So what I'm thinking about here, the next question I think is what's the p-value? So let's think about what we've got going on here. So I've got my distribution, sorry, jump the gun. Sample means will be centered around this value of $606.40. I found a sample mean of a 622.85, I think it was. So with a two-tailed test, I can find the probability that I saw something this far away from the assumed true value or even further that went against the null, right? And I might think, okay, that's my p-value. But for a two-tailed test, it was equally as likely for me to see something that was this far away from the assumed true mean, but below that equally went against that null hypothesis, right? So it was equally as likely for me to see something below that assumed true mean that would have went against my null hypothesis. Now before, when we had like, go to the other example we had. When we had the null hypothesis being less than or equal to, right? If instead of 71, I had found what, 63? Well, it would have been equally as likely for me to see 63 as it was to see 71. However, if I had seen 63, that didn't go against my null hypothesis. So for a two-tailed test, now if I think about the value that was equally as likely for me to see, well, now that value does go against my null hypothesis because my null is just exactly equal to this one value. So my p-value is actually, you can kind of think about it as the total area in both of those tails, or the probability that I see something this far away from that assumed true mean, or even further, that's the definition of my p-value. So if I've got two tails, and the kind of area in each tail, total area in the tails is my p-value, each tail will have half the p-value, right? So if I find one of them, to get my total p-value, I simply multiply by 2, right? And it would cancel out and give me the total p-value, right? So whenever I find the area in this tail, I have to multiply it by 2 to get my total kind of end result p-value. So what we can do is turn this into a z-value, right, or a z-statistic, use the tables to find this area to the right. Once I have this area to the right, multiply it by 2. Now, if it helps me to draw out that I know that there's a second tail over here on my standard normal distribution as well, you can do that, that's fine. But you only observe one sample mean, right? So you're only turning one sample mean into a test statistic. So if we use that equation for our test statistic, that we know gives us our test statistic. We plug in our sample mean that we found, the assumed true mean from the null and alternative hypothesis, our alpha value, and our sample size. We get a z statistic of 1.39. Right? So we get our z statistic here. It's 1.39. We want the area to the right. Okay? So we'll go ahead, look that up in our table. 1.3 all the way over 9, 0.9177. So I multiply that by 2 and I've got my p-value, right? No, right? Exactly, right? Because if I took 0.9177 multiplied by 2, I've got something over 1. The p-value is a probability, right? So the table told me the area to the left. I wanted the area to the right. And then I need to take that and multiply it by 2. Forget exactly what the number is. It's like 0.14, 0.1644 or something. I don't know, we'll see eventually, but it's about 0.16, okay? So I've got that here in the slides. What the exact, 0.1646, right? Okay? Oops, went a little bit too far. So we've got this p-value. What levels can we reject at? Well, I'm going to set up, instead of our typical values of 0.1, 0.05, and 0.01, if we use those benchmark alpha values, which levels could I reject at? Is 0.1,
95, right?
is 0.16 less than 0.1?
No.
It's not less than any of them, right? So I actually can't reject at any of my conventional levels here. I fail to reject at every kind of benchmark level. Now, if I go back far enough, I'll eventually find an alpha or a significance level I can reject at, right? If I were to use an alpha of 0.2, well, now that 0.16 p-value that we found is less than 0.2, so we could reject with 80% confidence, right? If alpha is 0.2, my significance level would be 20%, confidence level would be 80%. So here was the first example that we did. Here's the second example. I'm just kind of putting the p-values that we found. At the 80% confidence level, or 20% significance level, or an alpha of 0.2, I can reject the null for both of these. However, at the 10% significance level, when alpha is 0.1, or the 90% confidence level, I can only reject the null for that first example, not for the second. And then for both of them, neither of them could I have rejected at the 1% significance level or 99% confidence level. Where is it?
Example 1 on the alpha of 10.
Why am I missing this?
It's 0, 1, 2, 3, less than 1, 0.
0, 1, 3.
So the alpha level is 0.1, and then it's example 1. Up 1. Up. Over. Over.
Oh, I see. I see what you're saying. Sorry, I thought you were saying something else, actually. Hold on. I see what you're saying. I thought you were saying like the alpha didn't line up with one of these, and I was like looking at them like, no, I think they're all lining up, right? All right, sorry about that. Yeah. Any questions on either one of those or anything related to that? Okay with that? Okay. So I think we're going to do now, I think I might have said we're going to do some Excel work today. We'll probably hold off and just do all of that on Monday, because I want to make a point by the end of the class. Because what I'm going to go through now is I'm going to do hypothesis testing for proportions, right? So we just did it for the sample mean when we knew the population variance. Well, just like confidence intervals, we can also do hypothesis testing for proportions, right? It's going to be the exact same thing. It's just instead of assuming that the population mean is equal to, greater than or equal to, less than or equal to a certain value, we're going to assume the population proportion is equal to, less than or equal to, greater than, equal to a certain value, right? So we still have our same tests, right? Greater than, less than, or a right and left-tailed test, not equal to, or a two-tailed test. This is really just a little bit of difference in notation. Now, the procedure would be the exact same if we wanted to find the p-value, with the exception of our test statistical equation is going to be a little bit different. So what is our test statistical equation going to look like when we're looking at sample proportions? So before, we were looking at something like this, right? Where we knew the equation for the standard deviation of my sample means was the square root of my sample variance over my sample size. Well, now when we're dealing with proportions, we're going to take our sample proportion and subtract the assumed true population proportion, divide that by the standard deviation of my sample proportions. Now, the only thing here is now the equation for my standard deviation of my sample proportions. Well, remember with confidence intervals, we had to use this guy, which was sample proportion times 1 minus the sample proportion divided by my sample size. Well, we only did that because we didn't know what the true population proportion was. Well, we still don't know it, but we have an assumed true value for it. So instead of using that sample proportion, we're going to actually use the assumed true population proportion, right, when calculating the standard deviation of my sample proportions. Okay. So we're going to have a slightly different test statistic, but in terms of the steps that we follow other than that to find the p-value, we're dealing with proportions, so we can still use that standard normal distribution. Everything else is going to be the exact same. Okay? Now, I also mentioned, I don't know if it was last class or on Monday, we actually have two approaches we can use, the p-value and the critical value approach. We've only looked at the p-value approach up to this point. With these examples that we're going to work through for proportions, I'm actually going to show you how we do the critical value approach. Okay? So the steps will look almost identical, right? We identify our null and alternative hypothesis. We specify what levels of alpha we want to look at. Okay? Now, using alpha and the type of test that we have, right? So whether or not it's a right-tailed, left-tailed, two-tailed test, we saw how it changed things when we were finding the p-value, depending on the type of test. It'll also change our critical value. Once we find this critical value, we'll identify the rejection region. We'll then calculate our test statistic, which we now know is going to be, right, a little bit different than when we had a sample mean. We'll then compare the critical value to the test statistic. If our test statistic's in this rejection region, we reject the null. If it's not in the rejection region, we fail to reject. So visually, what we're going to be doing here is we're going to be looking at this standard normal distribution, right? Because we know that z statistic kind of is a z value, it comes from that standard normal. Let's do a left-tailed test first. So I'm going to find some value, and then everything to the left of it for my left-tailed test, or anything more extreme than that critical cutoff value. If I see a test statistic, right, if I say plotted my z statistic or my test statistic, and it's anywhere in this range, we call that range kind of my rejection region, right? If I see a test statistic or a z statistic over here, well, that's not my rejection region, so I would fail to reject the null. But if I see any test statistic in that rejection region, I reject the null. Okay? Now, another way that I typically draw this is once we find the critical value, the rejection region, kind of think about as going into the tail, right? Once I figure out what that critical value is, draw the rejection region just going into the tail. I haven't told you how to find these yet. I'm just setting up the idea of what we're eventually going to want to do. Now, you'll notice here, I would only reject if I see a z statistic that's less than my critical value, right? Because we're dealing with a standard normal distribution. So on the left side, these are all negative values. If I'm looking at a right-tailed test, I'm going to have a critical value over here on the right, and then I'm going to draw my arrow for my rejection region into that right tail. Okay? So for the left-tailed test, the rejection region, once we figure out what that critical value is, it's the area to the left is my rejection region. For a right-tailed test, once I figure out what that critical value is, it's the area to the right. Now, if I have a two-tailed test, we'll talk about this a little bit more detail in just a second. We're actually going to have two critical values, and the rejection region is going to be the area to the left of the negative critical value and the area to the right of the positive critical value. Think about that, critical value will be negative. Okay? So that's what we're kind of setting up, but how do we figure out what these values are, right? What are these critical values? Okay? So we talked about we're going to want to set up these rejection regions. The way that I actually figure out what my critical value is going to be is based off of the type of test I have. You can kind of see that through what I was drawing up there, but also what level of alpha I want. Okay? So, you know, you could think about it as if my test statistic for a right-tailed test, you know, I had it drawn and I erased it, or I drew over it. So let's think about, I think I set it for the left-tailed test, but not the right. Right? So for a right-tailed test, if my z-stat or my z-statistic, test statistic, is greater than my critical value, I would reject. But we said for the left-tailed test, if it was less than my critical value, I rejected. And kind of think about here, we have a problem with a two-tailed test because I can't really say if my test statistic is greater than or less than, because it kind of depends, right? So one easy way around this is no matter if we have a left-tailed, right-tailed, or two-tailed test, what we're going to say is that if I were to take the absolute value of my critical value, if that's less than the absolute value of my test statistic, that's when I reject. And that kind of covers the bases mathematically for each one of these scenarios. Excuse me. Now, I think personally, instead of like thinking about this absolute value thing, if you draw it out and just plot where your critical values are and plot where your test statistic is, it's pretty easy to see if it's in your rejection region or not. But if we want to be real formal mathematically, if you look at the absolute value of your test statistic or your z-statistic, and it's greater than the absolute value of your critical value, you reject. If not, you fail to reject. Okay?
So both of those are going to be like point whatever.
Not point whatever, right?
It's going to be those like 1 point something value.
Yeah, right? Because remember, the z-statistic or the test statistic is the actual z value. That's what I was using before to find my p-value, right? So my p-value was low, but my test statistic represented the number of standard deviations away.
Oh, okay.
Yeah. So it could be like 2 or 3. It could be.
So your critical value is to make sure you're like not so far away from mean.
Exactly. Yes, the critical value is making, well, I'll say a little differently. It's making sure that if you are rejecting, right, if I am rejecting, that I'm at least this far away from the assumed true mean. That's an excellent way to think about it. Yeah. It's making sure that I'm at least, the sample evidence I found is at least this far away. Yep. All right. I like the way you said that. So we kind of have it more formally written out here mathematically. Now, how do I actually find these critical values? Well, these critical values are coming from that standard normal distribution, so they are a z-value, right? And they're going to be the z-value that gives me my desired alpha in the tail. Now remember, alpha represents the probability I make a type 1 error, right? So what I'm really saying with these critical values is I want to make sure that I'm only going to be rejecting for test statistics. Well, here, I'll draw it out first, and I'll say that. So here's my critical value. Let's just do a right-tailed test. It's going to be the critical value associated with seeing kind of alpha in that right tail. Okay? So what it's ensuring is that if I see a test statistic in that rejection region, right? So here's my test statistic, that the probability that I saw that test statistic or anything more extreme is lower than the probability of type 1 errors I want to make, right? So to find that critical value, what we're really doing is looking up whatever area we want in that upper right tail. So let's say we wanted to do the 10% significance level, or 0.1. Well, if I use the table tells me the area to the left. I want 0.1 in my upper right tail. Then what I really want, I didn't mean to use a different color there, but what I really wanted was 0.9 in that lower left tail. So I'll go ahead, I'll go to my standard normal distribution. I'll look up the area of 0.9 in between these two values. So 1.28 and 1.29. Just like with confidence intervals, if you're doing this by hand, you're in between two values, take the higher of the two. So 1.29. Okay, so if we think about looking up that alpha of 0.1 for a right tail test, 1.29. And we're always going to find that same value, right? No matter what the alpha, I mean, if we look up the same alpha and it's the same type of test, we're always going to find 1.29. Now, if I had done this for a left tail test, it's actually a little bit easier, right? Because now I'm looking for a critical value that gives me that alpha of 0.1 in the lower left tail. Well, that's how the table's set up. So when I go to the table, all I have to do is look up that area I want in the lower left tail of 0.1. Whoops, actually I'll leave this up here. All right, the area I want in that lower left tail of 0.1. So now when I go to the table, I'll scroll up here. No, that's 0.01. I want 0.1, right? So it looks like it's in between these two. So negative 1.28 and negative 1.29. Take the higher of the absolute value, so negative 1.29, right? So notice, hold on. So notice the critical values I find for the right-tailed test are the exact same as for the left-tailed test. It's just that for a left-tailed test, my critical values will be negative. For right-tailed test, my critical values will be positive. Right? Which makes sense because remember, what's the mean of my standard normal distribution? 0. So if I'm looking up small values for alpha, well, for a left-tailed test, I know that those are all going to be negative z values that give me that. And for a right-tailed test, they'd have to all be positive z values. So right-tailed tests will have positive critical values. Left-tailed tests will have negative critical values. And the only other type of test we have that gets a little bit tricky is a two-tailed test. All right? So we had a two-tailed test. We're actually going to end up with two critical values, right? Because alpha is the total area in my tails now. So on each side, I have alpha over 2. So now when I want the critical value that gives me a total of alpha in my tails, there's alpha over 2 in each tail. If alpha is 0.1, right, there's 0.05 in each tail. So now when we go to the table, the values for our two-tailed test are going to be a little bit different than the values we find for our left and right-tailed test, okay? So if I look up that 0.05, I think the value I find, if I look up 0.05, I'm going to find the negative critical value. So if I go ahead and do that, I can get it here. Here we go. So I look up 0.05 in between these two, negative 1.6, 4 and 5, so negative 1.65. But I have to remember that I looked up and found this one. I also have a critical value over here. It's going to be the exact same, since this is a symmetric distribution, but positive. So for a two-tailed test, we actually end up with not just one critical value at every alpha level, but, there we go, pairs of critical values, right? A positive and negative kind of pair of critical values, okay? Now, I wouldn't worry too much about kind of the mathematics up here unless you're really curious. What we're really saying is, like, for a right-tailed test, these critical values will always be kind of positive. For a left-tailed test, always be negative. Two-tailed test, we're going to have a pair, okay? Any questions on any of that? Okay. Where are we at in time? All right. So to conduct this test, we're going to have to then plot this critical value, figure out our rejection region, then plot our test statistic against it. If it's in that rejection region, we reject. If not, we fail to reject. So even though I kind of started this discussion out with proportions, we could do the exact same. We can do critical value approach with sample means as well. It doesn't matter. We can use either the p-value or the critical value approach, regardless of whether or not we're looking at a sample mean or a sample proportion. Okay. And I've kind of already mentioned this. We can reject at these levels of significance. Alpha times 100 would give us a significance level. Okay. Already kind of went through this on the board, kind of drawing this for you. Here's just a summary of kind of what I had in the board, just if you're going back to the slides and you don't have that from your notes. Here's exactly what I was doing for the two-tailed, right-tailed, left-tailed test. It kind of reminds you left-tailed tests are negative critical values, right-tailed tests are positive critical values. Two-tailed tests, we have 2 critical values. Now, this picture writes them as z-values. I always when I draw it out, I plot them as CV critical values, but they are z-values. They're coming from that standard normal distribution. Okay? So we've got our steps, right? We could actually work through a problem here. Now, I flip-flop from the earlier slides, points 3 and 4. It doesn't matter which order you do it. If you find your test statistic first and then look up your critical values, or you look up your critical values and then find your test statistic. Order doesn't matter. What does matter is once you have them, you plot them against each other and see if your test statistic is in that rejection region. Okay? So let's work through this example. And this is kind of an extreme example just to prove a point with this hypothesis testing, right? So let's say you want to test the hypothesis for whether or not more than 50% of people own a gun, right? So you take 100 people, you find a sample proportion of 0.41. What's the null alternative hypothesis? Well, what I want to test for is in my alternative hypothesis, right? Because whatever I'm trying to test for, I assume the opposite is true. And that will be is my null. So if I want to test for whether or not more than 50% or greater than 0.5, the probability of people that own a gun is greater than 0.5, I then assume that the true population proportion of people who own guns is less than or equal to 50% or less than or equal to 0.5. So I've got another greater than sign here, so a right-tailed test, right? If I want to look up these critical values, right, which of these can I rule out right away?
D, because it has
D for sure, because that's a two-tailed test, right? That would be if I have pairs of critical values. If I have a right-tailed test, which of these can I also rule out?
because they're negative values.
Exactly, right? We said for a right-tailed test, our critical values have to be positive. Left-tailed test, they would be negative. Okay? Well, just to identify whether A or C is correct, I'm just going to look up one of them. So let's look up the 1% significance level. What would my critical value be? Well, what that's really saying is that I have a right-tailed test, and I want the critical value that gives me 0.01 in that upper right tail. So instead of looking up 0.01, the table always has the areas to the left. So the area to the left of the value I want would then be 0.99, right? Just 1 minus whatever alpha is. So I go to that table, standard normal table. I look up 0.01. Here we go. In between these two values, so negative 2.2 and negative 2.3. Well, if I did that, right, what mistake did I make there? I actually just looked up alpha. I actually wanted, right, 1 minus that because I had to do a right-tailed test. So I don't look up that 0.01. I have to look up that 0.99. I go down here. I'm in between these two values, so 2.32 and 2.33. Take the higher of the two, 2.33. Now notice if I looked up 0.99, I found 2.33. Whereas if I had only looked up alpha of 0.01, I found negative 2.33. So if you want to, if you can remember, you can always just look up alpha, regardless if you have a left or a right-tailed test. And then once you look it up, just remember, oh yeah, a right-tailed test, it's going to be negative 2.33, but it's going to be positive 2.33. But if you want to be real technical, the way that I have it up on the board there, where you look up 0.99, is really the technical kind of way to do it. So we could look up the other two as well. I'm not going to do it right now. We'll get more practice looking up these up a lot next week. But it would be the exact same process, but you would look up the alpha of 0.05 and 0.1, or the areas to the left there would be 0.95 and 0.9. Okay? So once we have these critical values, we then need our test statistics. So I'm telling you right now it's negative 1.8. And how did I find that? It's really just a matter of once you have that formula, you know that's the formula for your test statistic. It's just a matter of getting everything plugged in there correctly. So if we take the information from the problem where the sample proportion was 0.41, assumed true proportion was 0.5, we just have to plug everything in to that test statistic equation. Okay? So we got negative 1.8 as our test statistic. And here's our three critical values. So what would that really look like if we were going to try to set this up and do this? So I've got critical values of 1.29, 1.65, 2.33. Kind of draw arrows into the tails there to get your rejection region. Remember, this was the 10, 5, and 1% significance levels. Or 90, 95, 99% confidence levels. Well, if I plot my test statistic and it's negative 1.8, what levels can I reject at? Well, remember, when I draw these arrows, this is,
Oh, you can't reject it.
yeah, this is my rejection region over here. So my test statistic isn't even close to that, right? So I fail to reject at every level. But if I would have just taken a step back and thought about this from the very beginning, what was my null alternative hypothesis? So the null was that it was less than or equal to 0.5. My sample proportion actually supported the null here. So of course I should fail to reject it, right? I found something that supports it. Now, right here, we could have just stopped right away and said, yeah, I failed to reject the null based off my sample. But even if you work through kind of every single step, find the critical values, find the test statistic, plot the test statistic against the critical value, right? You'll come up with kind of the same decision, okay? Okay, we're good on time. Now, if I wanted to look up the p-value, this is going to be kind of a goofy one. But my p-value, it's a right-tailed test. So my p-value is actually anything to the right of my test statistic. So it's going to end up, I can look up negative 1.8. It'll tell me the area to the left of that. I can subtract it from 1. But we know this p-value is going to be really high, right? It's going to be something like 0.9 something, right? Well, if we only reject when my p-value is less than alpha, is this p-value going to be less than any of my benchmark alphas? Not even close. Just like the test statistic wasn't even close to being in my rejection region. Right? So why do these two kind of approaches lead to the same decision? So that's what I want to I wanted to get to today. I want to try to give you a good visual and explanation of why those two approaches are giving us the kind of same decisions here. All right. So I'm looking at that standard normal distribution. Right? When I find a critical value, it gives me alpha to the right of it for a right-tailed test. So all this would apply for left-tailed, two-tailed tests as well. I'm just going to use a right-tailed test because honestly, it's easier for me to write from this direction. When I'm finding a test statistic, right, let's say I have my z statistic, I can plot it here. For this right-tailed test, the area to the right of that would be a what? My p-value. Right? So notice my rejection region here for this right tail test critical value, draw my arrow into the tail. Anytime I have a test statistic in that rejection region, I should be rejecting, right? But anytime my test statistic is in this rejection region, notice what's also true. The area to the right of it, or that p-value, has to be less than this entire area of alpha, right? So that's why it leads to the same decision, because we're really just comparing kind of on different axes there, right? I can either compare my z values, the critical value, to my test statistic, or like you said, I'm kind of setting this threshold for I'm only going to reject if I see something that's even further away from that assumed true value than this many standard deviations. Really, it's a z value, so that many standard deviations. So if I see something that's even further than that, then I'm okay rejecting, right? Well, if I see something even further than that, well, then the probability I saw something further than that, or even further, is going to be smaller than that alpha value I set, or that I was comfortable with that level of type 1 errors, or that probability of making a type 1 error, right? So it's really just comparing kind of like on different axes there, okay? So any problem I have, I can do the critical value approach, or I can do the p-value approach, right? Questions on that? Maybe a glare spot so people are watching the video. Let's try to, there we go. Okay, that's actually exactly where I wanted to end today. We'll probably revisit this problem next class, work on another example, and then jump in and show you how to do this in Excel, okay? Your Excel assignments due at the end of the day today. Other than that, say if there's any questions for me. Okay, give me 1 second. If there's no more questions for me related to content or anything, then we can end, and I will see you guys on Monday. All right? Have a good weekend.